So next speaker is Stephen Holzen in UCLA, and we're just going to wait for him to share his audio and video. All right, Stephen, we're looking forward to your talk.
All right, thanks. The fractal, okay. All right, hi everyone. My name is Stephen. Thanks for being here today. So this talk is called Scaling Exact Inference for Discrete Probabilistic Programs. This is work that I did with Guy and Todd at UCLA. So the first thing I want to talk about is motivating the problem. So the problem we're tackling is discreteness in probabilistic programs. So many important probabilistic models are naturally discrete. So things from text analysis, network and computer network verification, other kinds of graph reachability, mixture models, medical diagnosis, and discrete Bayesian networks. These are all examples of problems that inherently involve discrete reasoning. And even today and over the past few days at ProbProg, we've seen some great talks that are starting to tackle discrete problems in Stan and in Hamiltonian Monte Carlo, and there's lots of other stuff. This is certainly not an exhaustive list of discrete problems or people that are tackling discreteness in probabilistic programs. And the key point here is that discreteness is very challenging for many existing inference algorithms. So today we're going to focus totally and completely on discreteness in probabilistic program inference. And we're going to talk about a new probabilistic programming system that we've been developing called DICE that focuses exclusively on discrete random variables. So it supports bounded integers, functions, Bayesian conditioning, a few other things that I'll talk about later. And it scales to hundreds of thousands of discrete random variables. So some of the programs it can handle are extremely large, on the order of megabytes in size. And we formally prove our inference algorithm correct with respect to denotational semantics. So you can check out our website, dyslang.cs.ucla.edu. It has a live demo that you can type code into, links to the paper, into the GitHub. It's all open source. So I'm going to jump into a motivating example of a discrete problem. So the problem we're going to talk about is a Caesar cipher, which is an encryption algorithm that's been used since antiquity. And the idea is that you swap letters. So E becomes B, D becomes A, and then that's your ciphertext. So cracking a Caesar cipher can be cast as probabilistic inference using something called frequency analysis. You assume that letters are drawn from the English alphabet, and then you use that to kind of infer what the key was. So you assume each letter is drawn from a well-known distribution of English letters. You can see it down here on the bottom left. That's like the histogram. And then you observe the ciphertext, the encrypted text, and you compute the posterior distribution on the key. So this seems like a nice, natural probabilistic program that we'd like to write. Probabilistic programs are great because we can represent such distributions and then reason about them automatically without making custom inference algorithms. So let's make this program. So maybe our ciphertext here is TVSFTVSK, which is ProbProg encrypted with some key. So here's the code here on the screen. We have a function, encryptCar, which takes a key and the observed ciphertext C. And first, it draws a character from this empirical distribution on the letters in the English language. Then it encrypts it, so it swaps it with the key. And then it observes that the ciphertext takes on a particular value sampled character. So that encrypt car is going to be like our workhorse. It's going to be encrypting each character one at a time and observing that it equals the ciphertext. Now down here, we're in the main body after the function. So we let k equal a uniform int, which is just a uniform prior on the key. We encrypt a bunch of characters, and then we return the posterior distribution on the key. So this is our example Caesar cipher program. The syntax here is sort of like ML or OCaml, if you've seen that before. This is the syntax of DICE. So let's walk through how a few different inference algorithms would tackle this problem. So first, let's talk about direct sampling. So does direct sampling work for this problem? And the answer is not very well, direct or rejection sampling. Drawing even a single accepted sample from the prior distribution of this program is very unlikely. So you can maybe sample some text QVD, KF, VSK from the empirical distribution of English text, and that's not going to be valid because it doesn't encrypt to the correct ciphertext. And similarly, we can sample many possible strings that we would like to encrypt, but the problem is that when you try to encrypt them, none of them equal the ciphertext. And in fact, only 1 out of 26 to the 8 is not rejected. Moreover, this program is non-differentiable, so some strategies that we'd like for improving our Monte Carlo inference algorithms that rely on differentiation, like HMC, not say DBI, are not applicable. And in general, sampling becomes rejection sampling in the worst case for many sampling inference algorithms. So this is a general problem with sampling on discrete probability distributions, which is that it's very difficult to draw a sample that ends up being accepted. So sampling has a hard time, and we can see that when we look at a graph of how long it takes to draw samples for rejection sampling. So this is to sample 10 characters, and we can see that at around 5 characters, it takes around 150 seconds to even draw 10 characters from this distribution. So that's not ideal. So next up, we might like to try some exact inference strategy. Because it's a discrete distribution, and moreover, it's a finite discrete distribution, we can actually enumerate all the possible states and compute the probability over each state. So this is nice because it's exact inference. So we're going to look at every single possible state and compute the probabilities over them. So that way we know that when we get the answer, it's going to be the exact right answer, which is nice. So let's look at path-based enumeration. So we branch on every possible random value. The problem with this, of course, is combinatorial explosion. So WebPeople has an exact inference algorithm. And if you run it on this program, translate it into WebPeople, you can see that at around 15 characters, you start to run into trouble. Things start to take 100 seconds, and we're exploding exponentially very quickly here. So what if we use something a little smarter than what WebPeople is doing? What if we do some dynamic programming and caching? So there's a probabilistic programming language called Psi, which implements some dynamic programming. And we can see that this helps substantially on this problem, but we can still only make it to about 100 characters or so before things start to get out of hand. And this is growing pretty quickly. So with Dice, we're going to be able to scale to on the order of 10,000 characters before we get to 100 seconds. Dice is scaling on this problem to extremely large examples. And it's doing so by exploiting the structure of the program. It's exploiting this repeated call to encrypt car. It's exploiting the arithmetic operations that it can directly encode. And now we're going to investigate Dice a little bit more and see how it can scale to such large programs. I'm going to give you some intuition for how Dice is working. So how Dice works. So I'm going to start with the summary of how Dice works. So we start with a Dice program, and we run it through the Dice compiler to get a binary decision diagram, which is a type of probabilistic circuit. So if you were there for Guy's talk about 40 minutes ago, he talked a little bit about probabilistic circuits and the kinds of tractable operations they support. So this is going to be the workhorse here. We're going to be able to do a lot of our reasoning directly on this probabilistic circuit. We're going to do weighted model counting on it, which is an efficient operation for probabilistic circuits to get our inference result. So this whole pipeline from end to end, we proved it correct. We gave a semantics to Dice programs, and we show that the inference result that you eventually get is going to match that semantics. So it supports Bayesian conditioning, functions, bounded iteration, tuples, integers, and arithmetic. So these are all finite programs. You're not going to be able to do loops that terminate with probability 1, for example. So that's one of the key limitations of Dice. We analyze functions modularly. So that's a nice feature of Dice. If you call the same function many times, it won't compile it repeatedly. It'll compile it once and reuse that result, which can yield some pretty significant benefits in performance. Okay, so the key workhorse behind Dice is factorized inference. So let's look at this simple program. It just flips 3 coins in order, and you flip each subsequent coin based on the results of the previous coin. So you flip X, it outputs 1 with probability 0.1. Similarly, Y, you look at X and you flip 2 coins, and Z, you look at Y and you flip 2 coins. And I've labeled them 1, 2, 3, and 4, and 5 just for the sake of exposition so we can reference specific coin flips. So we can compute the probability that this program returns true just by taking a sum over all possible assignments to X, Y, and Z. So if X is true, let's look at the first term on the far left. If X is true and Y is true and Z is true, you take the product of 0.1, 0.2, and 0.4, and that's one instance where this program can output true. We can factorize this sum, though. So this is not a great way of writing the sum. We're just kind of expanding every single possible branch in a relatively inefficient way. And what we can do is we can pull out some common terms from this sum. We can pull out this 0.1 from the first 2 terms and the 0.9 from the second 2 terms. And we can collapse this into a smaller representation. And as your program grows in size, these factorizations become very significant. And you can get exponential savings by factorizing things properly. Of course, you don't want to first generate this very large term above. You want to directly work in the factorized representation. And this is what Dice does. So then how can we find and exploit these factorizations automatically? That's going to be the engine that DICE uses. And the key idea here is to use logical translation. So it's the basis of well-known exact inference strategies from graphical models and probabilistic logic programs. And we're going to generalize this idea to apply to program constructs in DICE. So first we associate the program with a Boolean formula. So here I've written one such formula for this program on the left that we've been working in this example program. We'll call it phi ex. And it's just a bunch of logical variables that capture the values that these flips can take. So f1 corresponds to flip 1, f2 to flip 2, f4 to flip 4. And this formula is true if and only if the program is true. And I've written one example. So if x is true and y is true and z is true, we can see that one term in this formula is true, which means the formula evaluates true. So that's a key property of this formula. So that's one of the main things the DICE compiler does, is it associates programs with such formulae. Now we're going to manipulate those Boolean formulae so that factorizations are easier to find. So this formula on its own isn't going to help us do inference, really. It's just writing the program in a different but more convenient way. So the way we're going to do that is to compile it to a binary decision diagram. So we take this logical formula and we compile it to a binary decision diagram. And we can see the binary decision diagram here below. And we can see how this binary decision diagram corresponds with the formula. So if the formula is true, if the first term is true, f1, f2, f4 are true, we take this path through the binary decision diagram, and we end up with the true node here at the bottom. So BDDs are a compact representation of the Boolean formula. They try to do their best to capture and find repeated subfunctions in this. So for instance, if f1 is true, we get to this guy here. But we can see that both this arrow from f2 pointing and this arrow from f3 point to the same subfunction. So this is this caching and reusing thing that's going to make it so these BDDs can be smaller than a naive representation. Now we're going to take these BDDs and do something with them. So we're going to do what's called weighted model counting, which is a well-known exact inference strategy. This is the core of how they do probabilistic inference. You give a weight to each assignment to each logical variable. And then you can compute the probability by doing one bottom-up pass over the binary decision diagram, basically multiplying the probabilities in at each node. So in a sense, the small BDD is giving us fast inference. If we can compile this formula to a small BDD, then we can do weighted model counting efficiently on it, and then we can do fast inference. So I want to show you some examples of how DICE scales and how it performs on some programs, now that we've gotten a little bit of intuition for how it works. So here's an example where we compare against Psi, which is a probabilistic programming language that supports exact inference. We compare to it using dynamic programming, which we showed you earlier, and with their own built-in inference algorithm that uses some other strategies. So in general, these are Bayesian networks. So we've got some new benchmarks, these discrete Bayesian networks that we got by just surveying the literature of discrete Bayesian networks and choosing a representative sample. These are some very hard programs. They're actually really big. And I'll point that out on the next slide, just how big some of them are. Here we're computing a single marginal probability. So we just chose a leaf of the Bayesian network and computed a marginal probability of it. And in general, DICE does very well on this task. We can see that it's scaling. It's taking about a second to perform single marginal inference queries on some very, very large Bayesian networks. And size timing out, for any of the medium to large size Bayesian networks. So in general, DICE is going to be, to our knowledge, the best discrete probabilistic programming language for handling these kinds of discrete Bayesian networks. Okay. So what about a more challenging comparison? So we compared DICE against ACE, which is a discrete Bayesian network solver. It's specialized for discrete Bayesian networks. We can see how DICE is comparing against ACE here. In general, it's competitive on the medium-sized Bayesian networks. And on the extremely large Bayesian networks, ACE is still going to beat DICE. But I want to point out that this Munin program, this comparison here, is actually almost a 2 megabyte DICE program. It's really enormous. So we take around 400,000 4 million milliseconds to do this example. So it takes a while, but we could do it in the end. And I should point out there are some baseline benchmarks too that we compare against in the paper that I would encourage you to check out. I'm just highlighting these experiments here. Okay. So in conclusion, we have a new exact inference algorithm for probabilistic programs based on weighted model counting, and it's implemented in our probabilistic programming language DICE. It's fast, it's proven correct. And as future work, I want to point out, most programs are not purely discrete or purely continuous. They're actually usually a mixture of some. So as an invitation, I think it would be really cool to think of DICE as a core language for discrete reasoning that you can maybe embed in other probabilistic programming languages to kind of get the best of both worlds. And that way we can maybe handle some of these examples like mixture models or probabilistic networks with continuous priors and things like this that DICE cannot currently handle. Okay, and with that, I'll conclude. So this paper was published at UPSLA in 2020. So the paper is available on arXiv, and the website there is dyslang.cs at UCLA.edu.
Just unmute. All right, let's all thank Stephen for an excellent talk in chat. Let me see the camera. There we go. We do have a couple of questions, and we have time for questions. So I'll start with one of the questions from Pierre Denise. He asks, can you explain a little bit about these BDDs? And can these BDDs be generalized to any categorical probability distribution?
Yeah, sure, absolutely. So the binary decision diagram is a representation of a logical formula. So it's essentially taking it and writing it down in a way that makes it so that you can reason about it and do weighted model counting on it more efficiently. So it's just a way of, you can directly compile any logical formula into a BDD. There's lots of open source, very high performance libraries that let you do this. One example is CUD. So this is a well-known, data structure that's been around for a while. It's been around since the 1970s. So the second question was, can it represent categorical variables? The answer is yes. So DICE supports categorical random variables. It supports integers. It supports tuples. The way you do this is by defining an encoding from the categorical variable into a Boolean formula. And that's actually a lot of the work that DICE does for you. It actually comes up with these encodings, implements them in a way that is efficient. Like, for example, with integers, we represent them as binary encodings that we then, we generate an adder circuit that is literally an arithmetic adder that takes these binary inputs and performs the addition. So like that encoding is kind of the nuts and bolts of how DICE works. And that's a really important part of why it's so fast.
Great. So there's, I guess, a question that could serve as a follow-up question to this question. So given that you can represent kind of most forms of, well, all forms of categorical variables, can you also handle categorical variables with countably infinite domains?
No. Yes, that is a very important limitation of DICE. So we actually take the program and translate it into a finite Boolean formula because we generate a finite BDD. And that's how we do inference. So anything that would require an infinitely large Boolean formula doesn't work. So we're very, very laser targeted on this specific problem of finite programs that can have finite size Boolean formula.
Great. So there's one question about this particular example of the Caesar cipher. So that seems like an example you should be able to solve with, I don't know, component-wise Metropolis Hastings or something like that. What is an example that you've used DICE in where like your intuition is that, most of these existing approaches like simple component-wise MH wouldn't work? Right.
So that's a good point. So this Caesar cipher example is a motivating example. There are definitely different kinds of inference that would work on this, like Gibbs sampling would probably work on this Caesar cipher example. So in the paper, we have a few examples of variations of the Caesar cipher problem that would pose challenges for different kinds of sampling strategies. But in general, the sampling strategies are all going to either need to find a sample that eventually gets accepted, which in general can be combinatorially hard. So depending on how much work you put into that, the samples might be very hard to find, depending on how you structure the program. So that's part one for how sampling is different. Darn, I kind of lost my train of thought. That's my main answer to that question, which is that at some point when you're sampling, you have to find a sample. It's an arbitrary program, which in the worst case reduces to satisfiability. So that's, yeah.
Yeah. Okay. Somewhat, I guess, related question, right? So I think what you're showing is that the DICE scales very well in certain settings. Do you also have an intuition for kind of cases where DICE might perform very slowly relative to other approaches?
Yeah. So in the paper, we discuss in a lot more detail some of the other approaches. There's just so many different kinds of inference algorithms in a talk like this. It's very hard to give them all justice, right? I don't want to give the impression in this talk that we're just like, that we didn't talk about them in the paper. So in the paper, we talk about algebraic decision diagrams. So there are some papers that compiled algebraic decision diagrams that are very similar in structure to us, and we go through in a lot of detail exactly when these algebraic decision diagrams might be better than dice and why dice might be better than them. And in particular, for those examples, if there's a lot of symmetry in your distribution, like it's a discrete distribution it's a giant table with lots of identical rows, then ADDs might perform better. So dice is exploiting conditional independence in the program, and there are other kinds of structure that the program might have that dice isn't going to know about, and it might perform worse on those.
All right, then I think we'll do one more question, which is it potentially possible to compile dice programs to hardware circuits, given that everything is ultimately binarized?
Yeah, I mean, so a binary decision diagram, it can be written down as a logical circuit. It's a certain structure of and OR gates with negations in various places. In the tutorial that Guy mentioned earlier on probabilistic circuits, there's a bunch of visualizations in that tutorial on how you interpret various kinds of structured representations as logical circuits. And these logical circuits could, in theory, be written down using traditional logic gates like AND and OR. So there is a connection there, but I don't know whether or not that's a good idea. That remains to be seen.
Well, I guess maybe really, if I had to infer what the question asker is asking is, right, can you now also do fast hardware compiled inference, right, in this setting?
Yeah, I don't know. That's an interesting thought. It sounds cool, but that's not something I've really thought about or tried to do.
So yeah, so maybe the person who asked that question can follow up with Stephen online. Stephen, thank you again. We're going to move on to the next speaker,